Okay, gentlemen, let's start. So far, what we had talked is about some basic of machine learning techniques, and also, I guess last time we did talk about the basic of neural network, right? The deep feed-forward network, and also we did talk about um, how do we train the network using the backpropagation algorithms. And so today we are going to continue to develop the knowledge on that by talking about regularization. Well, that kind of terminology is quite hard to pronounce, but anyway, we we are going to discuss about this to show what kind of techniques we are going to apply in order to improve the efficiency in training a network. Because we know when you work with machine learning, we are trying to avoid a lot of overfitting problems. We don't want to train the networks so fit into the data because the real data may be very different from what we are seeing in the training. The training data just assembling set of something we see in the world. It's not really representing the world. And especially when you have a very limited source of data, then you have to consider how do you train the network so that we can reduce the error in testing phase, right? Okay, so that's what we are going to discuss today. And here are something we are going to discuss. Well, first, we are going to talk about some techniques related to the parameter normalizations. Uh, how do we normalize it and how do we penalize the, the difference or the magnitude of the parameters? And that's turned out to be very important. And also, we are going to talk about another technique related to constraint optimization. Well, in fact, it's related a lot to regularization too. And we are going to talk about data augmentations and why it's mattered to our training process. And maybe there are some other regularization approach that you may consider, but not necessary to be the baseline you are going to follow. And finally, we are going to talk about one of the most famous techniques in regularizations. It's called dropout. Okay, hopefully that you can get the idea from that. Okay, so first, let's talk about parameter normalization. Sorry, not normalization, norm penalties. So when you say about norm penalty, I mean, we are going to penalize the norm here. Well, based on this terminology, you can see that it can be L1 norm, but it can also be L2 norm. It depends on what you want to do. For example, if you have W is a vector of W1 up to WD, right? Then the norm 1, the L1 norm, or you may call it that way, will be the sum over the absolute of Wi given I from 1 to D, right? And if you are going to calculate the L2 norm, it's gonna be, well, the sum over, uh, let me say, Wi square, and that's it, all right? And so the L2 norm is kind of popular to many of you. And very often we penalize this norm by using the normal calculus techniques like the derivative, and it's easy for us to do so because the derivative is continuous, right? Now, why this matter? Because when you train the network, what you see is that the network is something that amplify the input, or maybe it will suppress the input, based on the value of the weight. And so if you let the weight to be something you cannot control, let the weight to be so small, what happens? If the weight is too small, then that means during the training process, when your input goes through one layer, it will get smaller, and that output will be fitted into another layer, and that will get smaller again. And if the weight is so small, then your output may be decreased until it's reached zero, and that's no good. Well, if that's not the case, and if your weight is so large you cannot control it, then saying about it, the output will be amplified from layer to layer, and that makes your final output too big so that it's kind of explode, and that's no good, right? If your output explode, then you actually have no control over the error, and therefore that makes a lot of problems in the training. So what happens here is we want to control the magnitude of the weight by putting some constraint on that, and that constraint very often will be represented by a functions on the weight, and we call this technique as norm penalties. Okay, so let's see what happens. So let me back with the original definition of regularizations. The problems we face a lot in machine learning is generalization, right? So think about it. You may train and you may want to make your training process to be able to generalize. So uh, you may interested in reduce the testing error, right? And reduce the testing error means using regularizations. Okay. Let's see. So this kind of terminology does not related to some specific algorithms. It's a collection of methods. Like you can think of regularizations like a set of methods that allow you to reduce the testing error. Now, when you try to reduce that testing error, you have to make a fair trade between the inductive bias and also the variance. Well, if you increase the bias, then you reduce the variance. If you reduce the bias, then you increase the variance. It's like there is no perfection here. We have to sacrifice one of them, okay? And that's matter a lot in training. So they say that an effective regularizer will try to balance this bias and variance and try to make the profitable trade. That means how to say it? Just a way to tell people that this is a good trade between the bias and variance. All right. So let me see how can I explain it. So you can look at the cost function or the loss function, whatever you look at. Then normally the loss function you are working on every machine learning models will consist of two terms. One is the main term, which is this one, right? It's measure the difference between what you predict compared to what you have in the label. Okay, so that's the main loss function or main cost, whatever you call it. The second term is the omega term over here. It's based solely on the parameters, and we call that one uh, the regularization term. Sorry for my misreading. I cannot read it correctly, but by that, you see that we have a hyperparameter uh, alpha. That alpha will control the weight of the regularization term. So suppose that alpha is small or maybe zero, then you only try to minimize the loss functions, the main loss function, right? But that may cause your model to be overfitted, and you actually have no control over the parameters value. But now, if you increase the weight of the alpha, you consider that penalization more seriously. And the way you define omega can be very different depending a lot on your final target, what you want to do with this. Okay, so let's see. Okay, so this is what we have so far. Normally, we try to employ that norm penalization like the L2 norm, like this one, the square of L2 norm. And they call this one with the very beautiful name, risk regressions term. Or maybe you can counter this one with another name called Tik Tikhonov. Yeah, Tikhonov, the Russian term, Tikhonov regularization. Well, whatever you call it, it's just the square magnitude of your weight matrix. And with that, when you take the derivative of the whole loss with respect to the weight, then obviously this gradient gives you this term. Sound familiar? The first one actually control the value of your parameters. So if you apply the gradient descent algorithms, then your final update will be the, the previous one subtract with the gradient, and if you combine that, it will go to this space. Now, what is this? The first part is similar. The second part is nothing but gradient descent, right? So if you polarize the parameters using this L2 norm, it's like you are trying to perform the stochastic gradient descent under the condition that you only keep a portion of your old weight, okay? And that's kind of similar to what we are going to talk in the optimization algorithms. It's like momentum algorithms, okay? So keep that in mind. We have something like that in our setting, okay? And let's see what I have here. Now, L1 norm is a little bit different, as you can see. For L1 norm, we have the sum over absolute value, and because of that, it's not easy for us to optimize because the derivative is discontinuous, and therefore it causes a bit of trouble, but not really because still we can do something with it using dual form or the psi function. But that's fine. We have some way to deal with it. And if you take a look at the gradient here, sorry, if you take a look at the gradient actually very simple. It's just the alpha multiplied with the sine of your weight matrix and then plus with the gradient. And so why we have L1 and L2? Because sometimes when you need the spare parameters, you use L1 instead of L2. Okay. Now L1 produce some solution is more spare than L2 because, well, I need to explain about this spare keyword. For example, you have some input here, okay, and you have to wait to compute the output here, okay. So suppose that the network is fully connected, then there are some weight from the input to the output. You have to multiply with the weight, right? So if you use L2 norm, every weight will have the value, will have the values, either big or small, that doesn't matter, it has some value. But if you choose L1 in the optimization process, if you choose L1, then it turns out that there are some weight has the value, but some other weight turn out to be zero. And this is great. If you have some weight that's not so relevant and after training it gets to zero and the other is not zero, then we have some sort of idea about the output. Now, the output based on a few input, not the every input. And also it's look like we are selecting some feature from the input to make the output, right? And that is why people call this R1 regularizations as a way to perform feature selection. That is interesting, right? Because in many cases, as you have so many feature, not every feature really play an important role in our problems. Okay, and that is why we have to consider about it a lot. Okay, so I hope you get that, and we will start from here. Now, given the regularization term and adding the that no penalization is very simple. But the question is, can we do better? Can we make it to some other extent and somehow related that one with something we already know? For example, constraint optimization is one technique we have been working on for a long time. Then the questions I'm having here is there any relationship between them? Okay, so actually there is. Let's see. Say you have the optimization problems. Training a neural network is nothing but using the optimization on the loss function, right? We try to optimize that loss function. And when it comes to that optimization, we have a concept called feasible point. Well, the feasible point is some point within the set S. Well, the set S you are seeing here is the set of values, okay, that potentially make the function fx you want to approximate to be maximal or minimal. And think about it. This is so abstract, but if you think carefully, this is like, all right, looks like the feasible points are some points in a set that makes the derivative of the function to be zero. Why? Because if you want to optimize the function f, then that should be the what should I call it? That should be the extreme. That should be the extreme of the function. Therefore, you are dealing with this point where to make the derivative to be zero. Then, in order to solve that, we have to constrain our parameters a little bit. For example, you may employ the constraint that you don't want your parameters to be larger than one. So in this sense, you may set up some sort of constraint like this. Then the problem now can be stated like this. Find the extreme of fx subject to the constraint x smaller or equal 1. But this is something we have known so far. And if you find a string of fx, then those feasible points should satisfy this kind of condition, right? Okay, so that's the setup we have so far. We can actually define the fx like the loss functions. This is the loss function, the main loss functions. And we can constrain our parameters to be a vector in the range of 1. And if that you know what to do, right, you can use Lagrange equation, which give you the Lagrange of x lambda equal to, well, the second term, the constraint, is inequality constraint, right? Then you should have f x subtract with lambda sum over, okay, I don't need that one, right? Yeah, if I'm using norm 1, then I should say norm of x minus 1, something like this. And this is my Lagrange equations. And you can go from there. Well, briefly, that should be what happens with the constraint optimization. Now, let's go a little bit more formal into the equations, what we have. Well, this material I described very carefully about the optimization process with respect to some constraint. But if you read some other documents, then you can also find very similar information. So what actually happens is, as you can see here, we have KKT optimization condition. If you want to optimize the function f with respect to some equality constraint g and inequality constraint h, then you end up with the Lagrange equations L, as you can see in equation number 8 I have over here. Okay, um, that's easy. We know that for a long time, right? So I hope that you still get it. In order to solve it, what we do is we are trying to maximize this Lagrange equation where we find the extreme with respect to alpha and lambda. But then we try to minimize the whole term under x. Okay, that's important. So if you are going to minimize fx, then you are going to minimize the maximum of L over alpha and lambda. That's what we learn in the optimization theory. I hope you still remember, even though it's a little bit very classic, but hope that we still remember it. All right. So the thing is, this is so important. If a constraint is violated, then the maximum of that Lagrange equation over alpha and lambda will be infinity. And that's important, right? So this says the Lagrange equation must always satisfy the constraint you employ on the problems. You cannot escape from that constraint. Okay. And they say, because of this, they say no infeasible point will ever be optimal. Every feasible point, a feasible point should satisfy the condition F and G. Then, if it violates the constraint, you cannot minimize it because the maximum of L is infinity, right? So that's the deal we have so far. Okay, so that's about constraint optimizations. I think there's no more we can discuss because for this one, it's so simple as you can see. The point is you can using constraint optimization like this one for penalize some parameters or putting some constraint on the parameters. In general, this constraint optimization can be uh, a little bit more general than the 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 idea you have before. The idea of the loss function include another regularization term. Okay, so we don't want that. We want something better. Now, when it comes to regularizations, then we have to talk about data set augmentation. Now, what is data set augmentation? We gather data from some sample we collect around the world, and not every single time you have big data. No, we just have a few sample. So in order to make this very uh, well, what can I say? Make it to a large data set. There's no way you can gather enough data. So the point is, if you cannot gather enough data, then why don't we fake the data to simulate the real world data? Well, a lot of people are trying to do so. Long time ago, if I recall correctly, there are some startup companies. They try to build a system that actually generate the data for you just for training. You put the request. Let's say I want a data set of some animals. Then please give me that data set. Then the companies will try to generate that list of animal for you and make it to a very big data set. And many of them are real, but many others are unreal. So the thing is, the bottom line is, you don't know exactly if your data is real or not. What you know is, okay, I may not have all the data, but many of my data may be generated from uh, models. Okay, that is why GAN is so popular. We will spend some time to talk about it. Okay, but for now, that's what we have. So basically, data set augmentation is a way for us to uh, edit more fake data into our data set. Hopefully that fake data simulates some sample we can gather around the world. For example, if you are working in NLP, then what can you do with data augmentation? May you make some, well, depend on problems. Let me tell you a few of them. So suppose that you are trying to build a system for autocorrection, okay, fixed typo in general. Then what you do is trying to, let's say, generate some typo. You have some sentence, and that is the correct sentence. Then from the correct sentence, you trying to generate some wrong sentence, okay, by disrupt some characters in the middle or replaced by some characters that nearby on your keyboard on the cell phone may be different from the keyboard you have on the computer and something like that. So you can adding some noise into your input and have a lot of real data just to fix the typo. Now, when you work in NLP and you have a problems of, let's say you want to classify the user intention, then you can actually add some template for that for that intent, and then you can generate a lot of sentence from the template just to make a lot of data. Okay, that's how we do data augmentation for text. For computer visions, we have many more techniques. For example, you take a look at the pictures, then you can generate some fake data just by translating the image around, and that gives you a lot of new data, even though you just have a single image, right? You can also add some noise into your photos. You can rotate your photos to make your model more invariant to that. And you can also have, let's say, um, yeah, look like you can, let me think, translate the color, yeah, strip the color around, or may you want to flip the image, or may you want to deform the object, transform it in some way like a file transform to make another view of the data and so on and so forth. So in general, we have so many ways to twist the image to make a lot of variants of the image. And that's good for our practice. I say so. So hope that it gives you a sense of data augmentation for visions. And of course, depends a lot on your problems. You may decide to do this techniques or that techniques. And there is no fixed formula. It just depends on the situation. Okay. Now, when it comes to speech processing, for example, what we can do? Well, you can do a lot of things actually. Think about it. If you have like um, the problems of voice recognition, for example, then you may gather a lot of speech around the world. Some of them require you to adding some noise. Well, many of voice you collect may be from the studio rooms without noise. And if you want to recognize that in the real world, then you have to add some noise. For example, some noise I have around here causing by some drilling machine, some noise caused by car and motorbike must be suppressed or must be added into my my voice. So by adding some noise into my voice, I do data augmentation. Okay, and also I can increase the speaking speed of my voice by uh, make my speech shorter, or I can make my speech longer, delay that time just to make some fake data. Okay, and that's the idea. That's the whole point of data augmentation. So in general, data augmentation is a very general term. It gives you some sense of how do we make data from the original data. Okay, and we use that a lot in practice, not just for experiment, but also in practice. So hope that all of you get the idea and apply it in the future. Okay, then here in the material, I did mention very clear about the idea of data augmentation. We try to create the fake data for training. Okay, that's the whole point. And for dataset augmentation, we see that it can be used for a lot of problems like object recognition, for example, is one typical problems that we can use data augmentation. Now for the image, you can adding a lot of variation, scale, rotate, alpha transformations, all kind of thing like that can be used to make the bigger data set. From one sample, you can make 1,000 if you want to, okay? And the basic techniques here is injecting the noise. And depending on the type of neural network, you can you can add more data to make your network more robust to the presence of noise. And there are many problems that can be trained unsupervised. And for example, you have like the denoising autoencoder here as a particular network. What it is receive an input. It's trying to encode your input into some sort of feature here. And then it try to decode that feature into the output. And the purpose of this denoising autoencoder is to minimize and calculate the loss function here. Okay, so as you can see here, I can have my clear image here. Okay, and from this clear image, I can, well, add with some noise. So this is Gaussian noise, maybe. You can add the Gaussian noise here or any kind of noise you want. Maybe the more noise you add, the better. And so if you add it, you can make this one, okay? That input will be the clear image adding with noise. And the purpose of the network is to encode and decode so that it minimizes the, the difference between the clear image and the output. That's the point, okay? So you are learning a way to denoise, to reject the noise of the original data. That's the very important application. And as you can see here, actually, if you take a look at this one, what happened is um, you don't have the noisy image, right? All you have is just a clear image you can gather around the world. And because of that, you have to generate some fake data. Okay, the noisy image is actually the fake data generated by you by adding some noise. Okay, and so this data set augmentation can help you to train this network better because you can generate an unlimited amount of data just to learn how to denoise. That's good, right? And in computer vision, as I mentioned earlier, you can apply several techniques like the affine distortion. Now, in affine distortion, you are going to apply the affine transform on your input. You can apply the sorry, the affine transform on your input image to make it look a little bit different, maybe a little bit bigger or smaller, shape a little bit here and there, sway it a little bit, adding noise, perform some sort of elastic deformation, and also shape the color, random translation, and so on. Okay, there are so many things you can do. Now let's talk about some other regularization approach and what we can do. Uh, you see here that in other regularization approach, we can employ some sort of semi-supervised learning. Well, this is one way to do regularization. It is unclear if we just talk about this kind of terminology. You have to observe this through some example, but for now, it's very abstract. I think even I don't prefer writing this line of description, but it's in the textbook, so we try to keep that idea. Okay. Now, in semi-supervised learning, we can also uh, try to learn some sort of representation that somehow better than the current one. For example, if you encode your image or your input into some simpler form, then maybe that simpler form can give you a way to classify or somehow uh, reduce a lot of noise, a lot of outlier from the input. That's really, really matter. And I think a lot of people don't aware of this because it's come to them very natural. They don't really care about the feature representation. But if you read some paper nowadays that mention about future learning, you will see this a lot. People tend to learn the future, learn about another way to representing your input rather than uh, analyzing the input itself. Okay. All right. So one of those semi-supervised learning you may know is PCA. I hope you still remember PCA. You use PCA to project your data onto some smaller dimension. Hopefully that that dimension can give you enough information to reconstruct the original data, or at least that representation is enough to classify, right? So that's the whole point. And if you think about it, you are reducing or projecting the data onto a smaller dimension uh, space. And because of that, maybe, just maybe, you are trying to filter out a lot of noise in your input too, without intention. Okay, you just do it like you smooth the data without intention, but you are doing that. Okay, and that's reduce the generalization error because, well, suppose that your input have a lot of noise, and if you project that data onto a new dimension and somehow you clear out that noise, then is that good? Yeah, why not? It's really good because now you actually have a cleaner data, and that make your model more robust to the input. Okay, so that's one way of regularizations, just a concept. Now, think about it. We have some way to construct uh, models. You know that we have the generative models that can generate from the distribution of the data. Okay, and if you can share that probability with the discriminative model, then uh, this will be very nice. So there is a trade-off between them. You may read about this in some other documents, but for now, I don't think it's really important. It's very long. Well, may I say it, too long. Uh, well, Actually, for me, I put the material here because I think this is important for some of you. So you should be able um, to make the answer uh, better for yourself when you read some papers, but unnecessary for our course at the current state because this relate to a lot of theory. So I just want to give you a reference. Okay. It doesn't mean you have to read in detail about this one, but if you want, find the books of Bishop and read about this one. And maybe you should take a reference on some other books of Ian Rockefeller also. But right now, that's enough. That's okay. So another way to do the regulations is to do multitask learning. And let me tell you this, a lot of problems in deep learning can be solved better by using multitask learning. And you take a look at this, what happens is we have the models, the model learns some share feature. Well, this hidden is the share feature. Well, if you train with one task alone, then that feature tend to fit on that task, right? So if you want that feature to be some sort of new representation can be used for other tasks, then you should employ the multitask learning. For example, I want to detect the object, but also I want to classify the scenes. Then, suppose that y1 over here is the object detection result. Oh, sorry, what's that? Suppose that this one is the object detection result, and suppose that y2 here is the scene classification result. Then what you want to do when you train both of them is to give the model a sense of how to classify a scene, but also how to detect the objects. And if you train one task alone, then detecting the object can be uh, very naive. For example, if I cut out the second branch that try to classify the scenes, and I only focus on detect the objects, okay, then think about it. One day, when you see something on the beach, will you classify that one as a car or a wheel or something? Suppose that I see some circle shape on the beach. Will I classify it as a circle, a shell, or something? Well, there is no context in that because you are dealing with the object detection only. But if you are training the model with along with the scene classification task Y2, then if I can classify this scene as the beach, then I know that the beach will not have some object like the uh, the wheel of the car or some uh, some sort of circle thing like the donut. I don't know, just some sort of idea. It very often not appear on the beach, right? So, oh, what's that? Sorry, I'm sorry. What's that? Sorry, guys. Okay, back to the topics. What we say is when you do multitask learning, we have some sort of idea about different tasks and the feature we learn when we do multitask training can help us to improve the robustness of the single task, every single task inside. And that's a good thing. Okay. So I recommend you guys to try the multitask learning when you solve some problems in deep learning. That would be very handy. And we have a lot of proof on this. Can read it. By proof, I mean we have a lot of paper talking about this, and you can take it as reference. Okay, so let's move on. This is one particular observation you may have when you do training a deep learning network. So when you train the network, very often you see that the training set loss will continue to reduce, but the validation loss will reduce up to some point here, and then it will start to stay there or maybe increase. So you may not interested in training the model further because this point at this point, maybe this is enough for us to stop. You don't want to train any further because it's lead to nowhere, and maybe why the training loss reduce, the validation loss increase, and that indicating that the model is not good, is overfit on the training data. Okay, so we better employ the early stopping techniques. That's not even a technique, it's just stop early. Okay, now when it comes to regularizations, parameter sharing is also one of them. You want to share the parameters. You don't want every output unit to be affect differently from the input. So you share the parameters. That's the whole point. And not just saving a lot of memory, you are also trying to reduce the overfitting phenomenon in your models. Okay. And one particular example of this is the convolutional neural network, which we will talk about in the next few class, I think. And yeah, that's what we are trying to say. Now, last regularization techniques we are going to talk here is dropout. What is dropout? Well, if you have to talk about dropout, you see that a lot of framework like TensorFlow or scikit-learn or PyTorch, they let you define a layer, okay? And in that layer definition, they have an option for you to choose. You can choose dropout to be some number from 0 to 1, like 0 0.5, 50% dropout, or 70% dropout, or 30% dropout. It's up to you. But you have that choice. So now let's see what dropout means. And in order to understand dropout, you have to understand about the assembling learning and backing. Backing is actually an And technique is a technique has been introduced in 1994. It's very old one. Okay, it's trying to reduce the generalization error by combining several models. Yes, that sounds good. This looks very similar to ensemble learning, right? You train a lot of models, and hopefully that the final result gather from all the models will give you more confidence in classification tests or regression tests, and that's it. So if you take the average output of all the models, then you have ensemble learning that we know. And in practice, people don't use ensemble learning, trust me, because it costs too much just to produce one output. So instead of doing ensemble learning, people tend to try out some techniques because especially for deep learning, we don't use ensemble learning. Ensemble learning only good if you have a small model. Okay, and let's see. First, let's talk about backing. For backing, what it is, we have an original data set. Well, 9, 6, and 8 here are some data in the original data set. I would call it the class of the data. Then, if I perform the backing, what happens here is I'm trying to put my hand into the bag and pull out some sample, some class of data. So look at this. If I randomly put my hand into the bag and pull out something, maybe I will get A, 6, and A. If you think about it, in terms of sample, you can look at it that way. But if you look at it at a bigger scale, you are sampling the class 8 twice and you're sampling the class 6 once. So looks like right now the data bias toward the class 8, but the point is after training this model, the model will learn to classify between number 8 and number 6 just by look at the circle on top. So what you see is if I found a circle on top, it's likely that I'm seeing number 8. And if I don't see the circle on top, it's likely that I see number 6, right? That's the future learned by the first model. Now for the second models, I again randomize, put my hand in the bag and then pull out something. Now this time I pull twice the class 9 and I pull one time class 8. So what happens here is it's look like the data is biased toward the class 9, but that doesn't matter. The feature I learned here is the circle on the at the bottom. If I found a circle at the bottom, I I can confidently tell you that this one is number 8. And if there's no circle at the bottom, I will say this is number 9. Okay. Now, as you have two model like this one, you can start doing a test of classification. Now, if you have number 8, you put into model 1 and model 2, you will get the output will always be number 8 because it satisfies the condition of number 1 having a circle on top. It also satisfy the condition of number of the second models having a circle at the bottom. So we have number 8 for both model, and you can confidently tell people this is number 8. Now the trouble comes when you put number 9 into the model. For number 9, the first model say 8 because it has a circle on top, but the second model say it is 9 because it has no circle at the bottom. Well, and because of it, you cannot make decisions for number 9. If you have a sample number 6, then the first model say, okay, this is not number 8, but I don't know what it is. The second number say, okay, you have a circle at the bottom, so you are 8. So one say A and one say not A. What can you do? You cannot do anything, right? So this is also a very classic issue we have with machine learning. Now, the reason why you use backing is you have more option to create the difference in the models. You can make a lot of difference models just by having different data. Okay, backend means you have a back, you pull data out to make a new data set, and given a new data set, you can train a model. Then you can train a lot of model this way, and it gives you different models. Hopefully, different models will classify your data in different way that is uh, going to benefit our final result. But again, as you can see here, it's not really good, right? Because we only have two models. Usually, the number of models should be some even number. Oh no, odd number, not even number. Sorry, because the final decision should be very clear. Yeah, that's is what I can tell you about backing. So it looks like every models here will learn the data in a different way and have different connection into the model. So what is dropout? Dropout also trying to learn similar to backing techniques, but instead of having too many models, it's learn all the models at once. It try to reduce the computational cost and trying to regularize a war family of models. So normally the dropout is not an ensemble learning, right? The backing techniques you see over there only good for 5 to 10 neural network, but more than that is turned out to be so annoying, and you need a lot of computing power to do so. That's no good. So we try to use dropout in this case. Okay. And this is the picture of dropout. So the left side give you the figure of a network with all the connection available. The right side show you a lot of different configuration you may have. We can have some missing link randomly, okay? And because of that, when you look at the models on the right side, you feel like, oh, if I have too many variation like this, how can I learn all of them at once? So Java say, okay, I will share the weight across all the network. The only difference is the the connection is either there or dismissed somewhere. Okay, and that's the main idea of dropout. We are going to randomly drop the link or the node. Well, I hope that you spend some time reading about this at home because there are some documents in TensorFlow and in PyTorch and scikit-learn. They will describe dropout in a very different way, and you have to be careful about that. Some dropout implementation, they let you drop some unit. Some dropout implementation say you can decide to randomly drop out the link. Now, what will you choose? Drop out unit means you are going to drop out all the weight associated with that node or that output, okay? And drop out link mean you randomly mask the weight, your choice, okay? Think about it. If I drop out a node, let's say I want to drop out this one, then all the link I have from that one will be discard. Then I only have the network with this three link. That's the node dropout. But if you drop the link, you can have some link like this one. Okay, and you may just drop one link. Then how to do that? We mask that link into you using a mask. We can clearly disable that link on the network, and that's your choice. So overall, when you try to do dropout, what you do is having some link disabled by using dropout depend on the framework implementation, or if the framework lets you to drop some unit, you can also do that, right? Your choice. And here are some summarization I have between dropout and backing. For backing, all the models are independent. Okay, they are not so related to each other. All the weights are different. The only thing that uh, really affect the models is the data you use for training. Now for dropout, because the model share the parameter, then most of model are not explicitly trained. And because of that, it is infeasible to sampling all the subnetwork in this universe. There's no way you can do so, right? Then well, I think for dropout, we make the assumption that we can learn some variant of your network, but unnecessary for you to um, apply or training on every possible network. It's unnecessary. Okay. And for this, let's talk about how do we classify the output. Well, if you have an output from the models, let's say Y, then will you trust that from the models? We don't know, right? Suppose that the model introduced the output to be the probability of the output Y given X. You may call it softmax or something, that's fine. Now, the models will give you the probability of Y given X, right? Then, if you have backing techniques here, then what you do is taking the average of that probability. That's all you have to do. For dropout, it's a little bit different. Now, let's say a submodel can be defined by the mass vector. So in this context, I'm talking about we are considering dropout as a masking technique. You don't really recheck the whole node, but you recheck some link to the node and out of the node. Then they say that a submodel can be represented by a mass vector mu here, mass vector mu, okay? And each submodel will define the probability distribution P, Y given X and mu because that define the models, right? The submodel, sorry. Then you have to make decisions based on the arithmetic mean over all the mass, right? Where P mu is the probability of the mass and P y given X P is the probability generate from the output of a particular model. You apply the mass mu. Well, this looks annoying because there's no way for you to calculate the probability of the mass and also compute this arithmetic means is infeasible. There's no way you can do so. Okay, it's like something we cannot do in our lifetime. But this is nonsense. But well, what you can do if you don't agree with this, what you can do normally. Uh, You don't know about the probability of the mass mu. And if you don't know, you just assume it to be some number. And you must pass your input into the model with different mass and then take the average of the output, right? That's also fine. But let me tell you, even if that is the case, then there's no guarantee that the average is correct. Also, another issue with dropout is how many is enough, and the runtime is matter. So, will you wait for passing the input to the model like 1,000 times just to calculate the probability of that label under the input X? You cannot, right? It is so bad to do so. You cannot wait for, let's say you pass one input and get the output in 1 second, and then you say, okay, wait, I need 1,000 seconds to pass that 1,000 time to get 1,000 output and compute the probability. And I will tell you the answer. The 1,000 seconds mean, wow, that's about a few minutes, right? No one will wait. So anyway, even though in theory you should compute the predictions as a mean over all the mass you have, but in practice, you don't do that. In practice, you don't do that. In practice, you randomize the mass and then you pass the input to the output. That's all. That's all you should do. Or maybe you just fit the output to the the input to the output by having no mask at all. Your choice. Again, theory is theory, but the the real situation is very different, and we may not apply this, right? As you see, the equation 13 here say that we should calculate it this way, but no one do that. Okay, and that's the problems. Randomize the mass and passing one input to the output, and that's it. That's one choice. The second choice you may have is using the full models and apply the input on the full model to get the output. That's all. So whatever you do, pick the right choice. And you have to read more about this in some documents. Well, I guess many of you didn't aware of this one, and many of you just consider dropout to be a component of the model of the layer, but you don't consider how do we use that after training. Of course, training is good, but what about testing? When you do test, what you do? You will also random drop, or will you use the whole weight? It's hard to tell, right? Okay. So that's a few things I just want you to remember. In practice, if you define that layer as a dropout layer, then in training you randomize the mass, but also in testing you should randomize the mass. And we don't really take the arithmetic means over the all mass because that's infeasible. Okay. Now, they argue and they say that the dropout is computationally cheap. Yeah, it's true. Okay. We can use dropout during the training and is required only the big O and for computation over every update. So that's good. You can do that over time. And the dropout does not limit the type of the models for training. In fact, it gives you ability to make your models look more diverse. Okay. And a lot of people now using dropout just like the basic layer after every few convolutional layers or after a few fully connected layer. Usually they will do dropout in FC layer or something. You have to take that seriously when you read the code. Well, it's hard for me to tell you where will they apply, but usually they apply the dropout in the a few last layer, especially after a few fully connected layers. They will apply dropout, but rarely they will apply it in the middle of the network. Unlikely to do so. Okay, keep that in mind. You don't apply dropout on convolutional neural network. Very rare. I saw some people do that, but not so often. So keep that in mind. And of course, using the dropout will reduce the cost of training a lot. And yeah, also, if you want it to be more efficient, you must increase the size of the models to have more variations. And yeah, they say this is the trade-off. You need, if you have a large model, you need more iteration to train because that's sure that it just come to us very natural. If you have a large model and you drop out some link or some unit in the models, in order to learn all the variation you have, you need a lot of iteration over the data. That's the point. Okay. And the final word for this is if you have a very big data set like ISVLC, some data set for image recognition, it's very big data set, then you don't need regularization. Okay. In short, if you have a lot of data in the world, you have time for training, then you don't need regularization because it does not really contribute a lot in the final result. Okay, that's the point. If for some reason you cannot gather enough data, you just have a few data, then uh, you need to consider dropout a lot. Well, in that case, the dropout is not so effective in small data set. That's weird. Should I use dropout or not? Because if I have a big data set, I use dropout and it give me no benefit. I don't use it, right? Now, if I don't have uh, a lot of data, I just have very few data, then again, the dropout is not so effective. What should I do? Well, this is a very interesting situation. If you have a lot of data, you don't need regularization, you don't need dropout. But when you have less data, you also don't need it because it's very ineffective. So you only use dropout when you have somehow adequate amount of data. Well, adequate amount of data is some sort of very abstract concept, and I don't think people will agree with me on that concept, even though they say very large data set or very few data sample. Those kind of words doesn't give you a concrete sense of how much is large and how much is small. No way you can tell, right? But that's the thing. And yeah, I think that's all about dropout. So hope that you get some idea about it. Again, when should we use dropout? When you have not so much data, not so less data, but mostly you are going to use dropout when you want to regularize your models, when you want to reduce the testing error by learning a lot of model at the same time. And remember, dropout is a way to learn multiple model at the same time. Okay, that's the main point. There's a lot to discuss about this if you read some paper nowadays. But for now, just leave it right here because I think that's enough information. Okay, so in the next class, we are going to talk about some optimization techniques, and maybe I will move on to another topics related to the convolutional neural network also. I will try to rush in the next few days, so you should get ready for that. Okay. For today, I think I should stop here. Sorry, my voice is broken. I talk a lot today, so anyway, thank you for joining. I will end the class a little bit early because my voice is broken now. I cannot speak any more. So, um, okay, thank you for joining and see you next time.